Welcome back to 3 Inquisitive Kids. In this video, we will be looking at linear Diophantine equations using the Euclidean algorithm. A Diophantine equation is an equation with two or more unknowns with integer coefficients, for which only integer solutions are of interest. Today, we're only going to be looking at linear Diophantine equations, so the variables that we will be looking at will only have a degree of 1. Let's start with some calculation problems. Find one integer solution set to the following Diophantine equations, and then express all the possible solutions generally. So there are two parts to this problem. Find one solution set, and then express all the possible solutions generally. So we're going to have to look for a specific solution and a general solution. Now the first step is to simplify this equation. As you can see, 2,173, 2,491, and 53 all can be reduced by 53. So dividing both sides of this Diophantine equation by 53, we get 41x plus 47y is equal to 1. And the next step is to check if there is a solution to this Diophantine equation. Sometimes Diophantine equations don't have any solution. So check for solution is our number 1 step. And the way we check for solutions is to see the coefficients, so 41 and 47 in this case, find their greatest common denominator, and see if that is divisible or if that divides evenly, and see if that divides evenly into the other side of the equation. So does the greatest common denominator of 41 and 47 divide 1? Well, it does, because they are coprime, meaning that their greatest common divisor is 1, and obviously 1 divides 1. So this equation indeed does have a solution. Now the next step is to use the Euclidean algorithm and we're going to find one solution. So how do we do that? Well, all we want to do is express 1 in the terms of 41 and 47. So we're going to start by taking 47, and we're going to write that in terms of 41 plus a remainder. So 47 is equal to 41 times 1 plus 6. Now you may have to look a little bit into the Euclidean algorithm in order to understand what I'm doing here, because the Euclidean algorithm is a solution for many number sense problems, a lot of modular arithmetic problems as well. The next step is to shift 41 and 6 to the left. So 41 is equal to 6 times 6 plus 5. Now shift 6 and 5 to the left. 6 is equal to 5 times 1 plus 1. And we can stop here because we know 1 is their greatest common divisor. Now the next step, using the Euclidean algorithm, is to just rewrite all of these equations, but in this case, we're going to isolate 1. So how can we express 1? Well, 1 is equal to 6 minus 5 times 1. And we're really trying to express 1 in terms of 41 and 47. So now we're going to use what we know from the left side and substitute in 6 and 5. 6 right here is equal to 47 minus 41 times 1. And we can replace with 41 minus 6 times 6. In the end, we will have the solution. 1 is equal to 41 times negative 8 plus 47 times 7. So this would be one solution set to the problem. Because now that we have expressed 1 in terms of 41 and 47, we see that this is the x value and this is the y value. Meaning that to the first part of the problem, our answer would be x, y. So one of the solutions would be negative 8, 7. That is one of our solution sets. But because this is a Diophantine equation, there is an unlimited number of solution sets to the equation. So the third step right here, I'm going to move to the right. The third step is to generalize the solutions using the special formula. So we're going to call this one solution set x0 and y0. So this is equal to -8, 7. Now, to find the general solution, all we're going to do is take x0, y0 plus n times b, a, where n is an integer. As for what b and a stand for, b is simply y's coefficient, and a is simply x's coefficient. So, for example, in our case, we had 41x plus 47y is equal to 1. In this case, 41 is a, and 47 is b. So a and b are just the coefficients, but here they are swapped. And here n is any integer. So basically, it's any multiple of b and a being added on to x and y. So in this case, if we were to plug all these values into the general solution of this Diophantine equation would be, we're going to have -8, so that's x0, plus bn, and b is 47, so 47n is our x value, and all of the y values can be expressed as 7 plus an, and a is 41, so 41n. This is the general solution that we are looking for. All solution sets of this Diophantine equation, the x can be expressed as -8 plus 47n, and all of the y values can be expressed as 7 plus 41n. So in the end, and also you can use any variable you want for n. So in the end, this is our general solution. Now, let's take a look at the next problem, and you may want to pause the video using these 3 main steps. Number 1, checking for solutions. Number 2, the Euclidean algorithm. And number 3, finding the general solution to help you solve this next one right here. Pause the video and see if you can solve this on your own. Alright, so here we are going to use the same steps, it's just that the values are a little bit different. Really, these are 2 really similar Diophantine equations. The a and the b coefficients are the same. It's just that on the right side, instead of 53, we have 159. But we can still simplify this. By dividing both sides by 53, we have 41x plus 47y is equal to 3. Now, the first step is to check for solutions. So number 1, is the GCD of 41 and 47 divisible by 3? And that is yes, meaning that there are solutions to this Diophantine equation. If this wasn't the case, then this Diophantine equation would not have any solutions. Number 2 is the Euclidean algorithm. Now we're going to use the Euclidean algorithm to find one solution. But in any case where the right side is not a 1, so in this case we have a 3, what we can do is still use the Euclidean algorithm that we got for 1, but then multiply both sides by 3. Let me show you what I mean. For example, in the end, after the first one, we were able to express 1 as 41 times -8 plus 47 times 7. So let's write that here. 1 is equal to 41 times -8 plus 47 times 7. This is really close to the second problem, except that we're trying to express 3 on the left side in terms of 41 and 47. So, since now we're trying to express 3, not 1, we can multiply 3 onto both sides. So here we multiplied by 3, which means on the right side we multiply by 3 as well. 3 can be expressed as 41 times -24 plus 47 times 21. So one of the solutions here would be x, y is equal to -24 and 21. This is one of the solutions to this Diophantine equation. But the next step is to find the general solution. Number 3, the general solution. So how do we do that? Again, we use this formula. So the general solution, I'm going to write it again, is x0, y0 plus n, where n is any integer, times the coefficients b, a. Now let's plug in the values. Well, we know that in this case, x0 is negative 24, and we're adding on bn. But what is the second coefficient here? B is just the coefficient of y, and in that case, it's 47. So plus 47n, and y0 is 21. So 21 plus an, and in this case, a is equal to 41. So 41n. This is the general solution of the second Diophantine equation. So using these 3 main steps, we can solve any linear Diophantine equation using the Euclidean algorithm and then applying the general formula. Using the information we just learned, let's take a look at the word problems. A small clothing manufacturer produces 2 styles of sweaters, cardigan and pullover. She sells cardigans for $31 each and pullovers for $28 each. If her total revenue from a day's production is $1,460, how many of each type might she manufacture in a day? So when we see the word might right here, it's just saying give one possible solution. But in this case, we're going to try to challenge ourselves and find both one of the solutions and the general solution. But this is a word problem, and we only know how to solve linear Diophantine equations. So let's rewrite the information we know first into a linear Diophantine equation. Let's set C as a number of cardigans she sells, and P as a number of pullovers she sells. So $31 per cardigan plus $28 a pullover is equal to a total of $1,460. So this is a linear Diophantine equation. Now we're going to try to solve. The first step here is to check if this equation does have a solution. Well, the greatest common divisor of 31 and 28 is 1. So it means that there is a solution to this equation. Now, because the right side, 1,460, is not 1, let's first just try to express 1 in terms of 31 and 28. Using the Euclidean algorithm, and because that takes a long time, I'm just going to write the final ending here. We can express 1 as 31 times negative 9 plus 28 times 10 minus 1. Then we multiply 1,460 on both sides of this equation. So now we have 1,460 is equal to 31 times negative 13,140 plus 28 times 14,600 minus 1,460. As you can see here, we already have our first solution set. x0, y0 is equal to negative 13,140, 14,600. But does this really make sense for the problem? She can't sell a negative number of cardigans. Now we already have a solution. C0 and P0, so the number of cardigans and pullovers she may sell in one day, is equal to negative 13,140, 14,600. But does this really make sense? She can't sell a negative number of cardigans in one day. So we have to use the general solution and then use that general solution to find another more specific solution that makes sense. So now we have to use the general solution. Remember, the general solution is just x0, y0 plus n times b, a. So here, instead of x and y, we're using c and p, but they mean the same thing. The general solution is negative 13,140 plus bn. So b, in this case, is 28 plus 28n, comma, and y, so in this case p, it can be expressed as 14,600 minus 31n. That's our general solution. Now the final step here is to find a specific solution that works. Let's start by looking at cardigans. So by looking at cardigans, we know that 31c is congruent to 1,460 mod 28. To solve this, we can simplify it into 3c is congruent to 4 mod 28. And now we multiply the inverse on both sides. Because the inverse of 3 mod 28 is equal to 19, multiplying 19 on both sides, we have c is equal to 4 times 19, which is equal to 76 mod 28. But 76 mod 28 is the same as 20 mod 8. So 20 cardigans would be 1x value. And the same thing for pullovers. We know that 28y is congruent to 1,460 mod 31. So if we take the mod 31 on both sides here, we can simplify it into 28y is congruent to 3 mod 31. And because the inverse of 28 mod 31 is 10, multiplying 10 on both sides, we have y is congruent to 30 mod 31. So 30 is another possible value for y, or in this case, p, because p is equal to pullovers. So how many of each type might she manufacture in one day? She might manufacture 20 cardigans and 30 pullovers. You can also double check to see if this solution does indeed give her a revenue of $1,460. Number 3. A piggy bank contains 24 coins, all of which are nickels, dimes, or quarters. If the total value of the coins is $2, what combination of coins are possible? The first step is to write this as a Diophantine equation. Let's set the number of nickels as n, the number of dimes as d, and the number of quarters as q. N plus d plus q will have a total of 24 coins. And if we write their values in terms of cents, we have 5n plus 10d plus 25q is equal to 200. So this is our system of equations. But to get rid of n, we can just multiply both sides of equation 1 by 5 and then subtract that from the second equation. So if we were to subtract 5n and 5d and 5q from the second equation, we would have 5d plus 20q is equal to 200 minus 120, or 80. Now we can simplify this even more and get d plus 4q is equal to 16. In the end, this is our final Diophantine equation that we can start trying to solve. The first step is to see if it does have a solution. Well, the GCD of the two coefficients, which in this case are 1 and 4, is in fact divisible by 16, which means that there is a valid solution. Now the next step is to use the Euclidean algorithm to find the one possible solution for this Diophantine equation. Well, because the right side we have 16, not 1, we can start by writing 1 in terms of 1 and 4. So 1 is equal to 1 times 1 plus 4 times 0. Then we scale things on both sides by 16. So we can rewrite 16, which is the value we are trying to rewrite, in the form of 1 times 16 plus 4 times 0. So as we can see, D0 and Q0, our first set of solutions here, is 16, 0. Therefore, the general solution would just be 16 minus 4n plus n. This is our general solution. Now the next step is to find one possible combination. Now we already know that this would work if we had 16 dimes, 0 quarters, and if we resubstitute these values in, 8 nickels. So this would be one possible solution. In another case, if they said we had to have at least one of each type of coin, let's say we had 1 quarter, then we would have 12 dimes or 11 nickels. Now there's so many other possibilities and sets of solutions that also pertain to this general solution. But these are just some examples that we can all answer the question with. A farmer purchased 100 head of livestock for a total cost of $4,000. Prices were as follows. Calves, $120 each. Lambs, $50 each. And piglets, $25 each. If the farmer obtained at least one animal of each type, how many did he buy? The first step is to express this information algebraically. Let's set the number of calves as C, the number of lambs as L, and the number of piglets as P. So we know that C plus L plus P gave us a total of 100 animals, and their values were $120 per cow, plus $50 per lamb, plus $25 per pig, giving us a total of $4,000. Now, to make this a Diophantine equation, we can first eliminate one variable. If we subtracted 25C and 25L and 25P from the second equation, we would have 95C plus 25L is equal to 4,000 minus 2,500, which is $1,500. We can simplify this even more by dividing 5 on both sides. So 19C plus 5L is equal to 300. So this is our final Diophantine equation. Now the first step is to check if it has a solution. Well, the greatest common denominator of 19 and 5 is equal to 1, meaning that there is a solution. Now from here, we can use the Euclidean algorithm. Expressing 1 in terms of 5 and 19, we have 1 is equal to 5 times 4 plus 19 times negative 1. Now we have to multiply both sides by 300 and scale it to the original number because the right side here is indeed 300. So now we can express 300 in terms of 5 and 19. 300 is equal to 5 times 1,200 plus 19 times negative 300. We can express 1 in terms of 19 and 5. 1 is equal to 19 times negative 1 plus 5 times 4. Scaling both sides to 300, which is the original number we're trying to write in the form of 19 and 5 with, we have 300 is equal to 19 times negative 300 plus 5 times 1,200. So from this, we see that one possible solution for C and L could be negative 300 and 1,200. Now to find the general solution, what we can do is using the original formula, C comma L is equal to negative 300 plus 5n, and y values can be expressed as 1,200 minus 19n. Now the next step is to just solve for specific solutions. Where do we start? Well, through observing the general solution, we see that 19c has to be congruent to 300 modulo 5. So therefore, 4c is congruent to 0 mod 5, meaning that c must be a multiple of 5. Now, since c can't equal 0, let's try c is equal to 5. If c was equal to 5, then L would be equal to 41, and P would then equal 54. That is one solution. Another solution is if C was equal to 10, another multiple of 5, L would equal 22, and P would equal 68. This is another solution. Finally, we have if C is equal to 15, and L would be equal to 3, and there would be 82 piglets. Now these are the three possible solutions, because if we went any further, L or P would not be answers that made sense. Remember, they have to be greater than 0 and a whole number. So these are the three solutions for the fourth problem. How many ways are there to make $200 from 1,000 coins, each of which is a quarter, dime, or nickel? The first step is to express this information algebraically. Let's set the number of quarters as Q, the number of dimes as D, and the number of nickels as N. So we know that the total number of coins is 1,000. So Q plus D plus N is equal to 1,000. Their values, 25Q plus 10 cents per dime plus 5 cents per nickel, is equal to 20,000 cents. So we can simplify this using previous methods into the Diophantine equation. 4Q plus D is equal to 3,000. This is the linear Diophantine equation we are trying to solve. And the first step is to check the greatest common denominator. Well, the greatest common denominator of 4 and 1 indeed does divide 3,000, meaning that there are solutions to this Diophantine equation. Now the next step is to use the Euclidean algorithm. We can first write 1 in terms of 4 and 1. So we can rewrite this as 4 times 0 plus 1 times 1. Now scaling both sides so we can get to 3,000 and rewrite that in terms of 4 and 1, we have 3,000 is equal to 4 times 0 plus 1 times 3,000. Therefore, we know one possible solution. So Q0, D0 is equal to 0, 3,000. All x values can be expressed in forms of t, and all y values can be expressed as 3,000 minus 4t. So this is the general solution. And now it's saying how many different ways are there to create $200 from 1,000 coins. So there is a fourth step to this problem. By writing D and N in terms of Q, we have from the original system of equations, D is equal to 3,000 minus 4Q. We got that from here. And N can be rewritten as 3Q minus 2,000. Now these values both have to be greater than or equal to 0, so because we can't have a negative number of coins. So 3,000 minus 4Q, or D, must be greater than or equal to 0. And 3Q minus 2,000 must also be greater than or equal to 0. This means that Q has to be less than or equal to 750, while Q must also be greater than or equal to 667 for all integer solutions. Now the possible values of Q go from 667 to 750 inclusive. So in here, in total, there are 84 solutions. Therefore, there are 84 ways to create $200 out of 1,000 coins, each of which is a quarter, dime, or a nickel.